Hi everyone. So in this video we are going to solve this particular question which was asked in GATE 2016 examination. It is based on data converters, and from data converters it is based on ADC, analog to digital converter. So we will solve this question. We will understand the meaning of each block. We will also understand what is the meaning of thermometric code. We will also understand what do you mean by thermometric to binary conversion. We will understand the meaning of each line. But before that I will give you one important concept which you might not be knowing. So what your ADC does? What is the job of ADC? It will take an analog input. It will take an analog input and will give digital word as the output. Let's just say I apply 2.1 volt and I am receiving 010. For 3.1 volt I can receive different code which could be 011. So with respect to analog input, it will give me a digital word of output. This is what your A to D converter does. But tell me one thing, let's just say if this is my V in. If this is my V in. V in with respect to time. If this is my V in, then this V in will be fed to the input of ADC. Is that so? What is fed at the input of ADC? Analog input. So V in will be fed at the input of ADC? No, V in is not fed at the input of ADC. Why is that so? Look, this ADC will have some finite conversion time. For dual slope ADC it would be different, for counter type ADC, for SAR type ADC, for flash type ADC. All ADC will have different conversion time. So it will take some time to convert the analog input to digital word. If I am applying 2.1 volt at t equals to 0, then I am not gonna receive 0010 at t equals to 0 only. It will take some time. It will take some conversion time. Now let's just say if I apply this input here, then what will happen? At t equals to t1, assume that this is my 5 volt. So I am applying 5 volt here at t equals to t1. So now what this ADC will do? This ADC will start converting 5 volt to the digital word. It will start converting 5 volt to the digital word. So this is the job of ADC, but it will take some conversion time. Let's just say the conversion time is 2 seconds. So it will take the time of 2 seconds to convert this 5 volt to digital output. So from 5 volt to getting digital output, it will take 2 seconds of time. But what will be happening at the input? At the input, the very next second, my input will be changing to 5.2 volt. At 0.1 second only, my input has changed to 5.1 volt. Now, if my input has changed to 5.1 volt, what will happen? At the input, you are seeing 5.1 volt, and now your ADC is processing 5 volt only, because 5 volt was applied at t equals to t1. Now, at t1 plus 0.1 second, input has changed. But currently it is processing 5 volt only. It will give the digital output after 2 seconds. So let's just say the digital output for 5 volt is 101. So it will give 101 after 2 seconds. But at the input after 2 seconds, this might be the input or this might be the input. So after 2 seconds, at the input you are having 4 volt, but output you are getting corresponding to 101, and in between this much value would have come. 5, 5.2, 5.3, 5.4, 5.6, 5.7 or 5.1, 5.2, 5.3 again, and in these much values would have come. So input is continuously changing, but it is still processing this 5 volt for 2 seconds. So what did you understand by that? That input of ADC should remain constant for a particular time, so that it gets some time to process that particular input. That means this 5 volt should remain constant for at least 2 seconds. Because conversion time is 2 seconds. So at least for 2 seconds it should remain constant. After that input can change. So for this process, before ADC we always use sample and hold circuit. Always sample and hold circuit will be used before ADC. Now what is the meaning of sample and hold circuit? So here never V in will be applied. Here VA will be applied, which will be coming from the output of sample and hold circuit. So what this sample and hold circuit will do? Okay, so let's check that out. So I will again redraw my V in. This is my V in. Okay, I am starting from t equals to 0. Let's just say this voltage is 3 volt. Now my conversion time I am assuming it 2 seconds. So now this 3 volt should stay constant for 2 seconds at least. This we have understood. That if it is changing continuously, then what will happen? This ADC will not be able to process these much of data. So it needs conversion time of 2 seconds. So at least 3 volt should be constant for 2 seconds. So what I am gonna do, I am gonna sample this signal with a time window of 2 seconds. What do you mean by sample? Sample is like clicking picture. I am here, okay? I click the picture at t equals to 0. So the next picture I will click at t equals to 2 seconds. Let's just say here, this is my t equals to 2 seconds. So the next picture I will click at t equals to 2 seconds. And the next picture I will click at t equals to 4 seconds. This is my t equals to 4 seconds. So this is what sample means. Next picture I will click at 6 seconds. What do you mean by sample and hold? That means I have clicked this picture. I have clicked this picture at t equals to 0 second. So if my sampling time is 2 seconds, that means this picture will remain there till 2 seconds. So at t equals to 0, I got 3 volts. So that will be remaining till the next sample. Now next sample I am calculating at 2 seconds. So let's just say this sample was 5 volt. So this 5 volt will remain there till the next sample. Next sample I am getting at 4 volt. So let's just say this sample was 4.8 volt. So this will remain there till then next sample you get at 6 second. So let's just say it is 2.8 volt. So till the next sample you will have 4.8 volt only, and then now you are calculating another sample. Now you will have 2.8 volts. So what did you understand? If I am sampling and holding it, that means for 0 to 2 second, I am having 3 volt only. For 2 second to 4 second, I am having 5 volt only. For 4 second to 6 second, I am having 4.8 volt only. And in that manner I am going. Now what is this? This is known as VA. And this is fed here. That your input should, the analog input should remain constant for a particular time. So what did you get to know? That your sampling time should be at least greater than, or in the worst case equals to TC. Very important observation, very important, you will say very important formula, I should not say, very important observation only I will say. So very important observation which you need to remember, that your sampling time should be greater than or equals to the conversion time. Because if it is lesser, that means let's just say if I am calculating the sample here at t equals to 1 second, then what will happen? The input will change at t equals to 1 second, but it needs the conversion time of 2 seconds. So it will be processing 3 volt at t equals to 0 till t equals to 2 seconds. It will be processing 3 volt, but input has already changed. So that should not happen. When it is processing 3 volt, the input should remain constant at 3 volt. Right? So always the first block of ADC is sample and hold circuit, which is not usually shown. But you should know that this particular input is coming from the sample and hold circuit. Okay, so this is the concept which I wanted to deliver. This we have already studied in our course only, but since I will be uploading this video on YouTube, so that's why I am explaining it again here. So now let's come to the question. So what this question is saying, that there is an input voltage, it has a input resistance as well, that is 75 ohm. Okay, and this node, these nodes are connected together. So in a comparator, negative node is connected together and positive node are connected with some reference voltage. Okay, now the op-amp is having an input capacitance of 8 picofarad. What do you mean by that? Look, op-amp are made from some MOSFETs or BJT. It would be made from some MOSFETs or BJT. This is how your op-amp would be made. And MOSFET and BJT will have some input capacitance. Like all the components, be it MOSFET or BJT, they will have some input capacitance. So that will effectively become the input capacitance of op-amp. So all these op-amps are having any ICU design on a chip, all will have some input capacitance. So these op-amps are having some input capacitance. So how these input capacitance will be connected? So this is your op-amp. This is connected to a fixed potential, that is Vref. So input capacitance would be connected here, right? So this node is common to all, right? This node is common to all. So from this node to ground, 8 picofarad capacitance is connected. So let's just say I am making this node. From this node to ground, 8 picofarad is there. From this node to ground, 8 picofarad is there. In that manner, a lot of 8 picofarad capacitance are there. How many 8 picofarad capacitance are there? How many comparators are there? How many comparators are there? There are total 255 comparators. So how many total capacitance will be there? 8 picofarad in parallel to 8 picofarad in parallel to 8 picofarad. This node is common. From this node to ground you are having 8 picofarad and all are in parallel. So 255 into 8 picofarad. So this much capacitance is there. Say yes or no. Now this node is connected to 75 ohm and then V in. Basically the scene is, this is your V in 75 ohm and then this node is common to all. So all the capacitance are coming in parallel. V in 75 ohm and from this node to ground you are having 8 picofarad and 255 are in parallel. So 255 into 8 picofarad. So this would be your capacitance value. This I am calling as R. Now what will happen? Let us say V in some voltage. So that will take some time to rise here, no? That will take some time to reach here. So what they are saying? The input must settle to an accuracy of half LSB even for a full scale input change for proper conversion. Now I saw at YouTube in some videos, they were saying that here it should be output. No, it should be input only. They are talking about this input. It should not be output. What they are saying, this particular input of the comparator, one input of the comparator is VREV, other input of the comparator is this node. This node I am calling as X. So this node I am calling as X. All these nodes are X. So this input of the comparator should settle to an accuracy of half LSB even for a full scale input change. So if my input is V full scale, then what should be my output? What they are saying? So X should settle, ideally X should settle to V full scale. But accuracy of half LSB means it can take the error of half LSB. It can take the error of half LSB. Ideally, it should settle to full scale only because this full scale will be charging this capacitor. But you know one thing, that to charge this capacitor completely, it will take infinite time. So at least it should settle to half LSB accuracy. That means it can take half LSB of error. Just as, let's just say my half LSB value is, wait a second, half LSB of full scale, half LSB of full scale, half LSB even for a full scale. So you can write plus minus half LSB as well. So basically this much of error it can take. Now just as we reach this value, just as at node X we reach this value, this comparator will be in condition to give the output. Are you getting this point? At the comparator input is changing. If at the comparator input is changing, so there is the chance that the output will change. But now what the question is saying, that if the input is changing, if the input has reached to this value, at that time comparator will be giving the output and those outputs will be taken by this digital circuit and we will receive corresponding digital output. Are you getting this point? Until we reach this point, until this node X reach this point, we are not in position to give the final output. So when we will come into the position to give the final output, when our X becomes this much. So what do you think, what is this? Like it will take some time. How much time it will take? What will be the equation of xt? Equation of xt will be Vfs e to the power minus t by rc. And I am saying that at t equals to t1, my X will be this much. At t equals to t1, my X will be this much. So what do you think, what is t1? I am saying that at t equals to t1, my X will be this much of value. So then what do you think, what is your t1? T1 is the conversion time. Ideally flash type ADC has zero conversion time. If everything is ideal, zero conversion time, just as you apply the input, comparator will give the output that will be fed to a decoder and we will receive the digital output. But here the scene is input capacitance are coming. That means the input Vref is stable, but input at the other node, at negative node, that is not stable. So we have to stabilize that particular input. If this resistance was not there, then what would have happened? Even though there is some capacitance, then still this input would have been stable. Directly input will be exposed. So all the output you will be getting at t equals to 0 only. If all the comparator delay, if this thermometric code conversion delay, if all delays are 0, so just as you apply the input, you will receive the digital output. But here there is some resistance, so this input is being stable after some time. And what they are saying, just as the input becomes stable at this, your comparator will be in action. Your comparator will be able to give the output. And if it is giving the output, at that time you will see the digital output. If comparator is giving the output, that is fed to this digital circuit and you will receive the corresponding digital output. Look, comparator is always in condition to give the output, but when you are going to check, this line states that when your x has reached to this much of value, at that time I will check my digital output. This is what this line is saying. So conversion time is t equals to t1. Are you able to understand this point? Are you able to grasp this particular line? This is the most important line. Vin is there, 75 ohm is there, this much of capacitance is there. This capacitance will take some time to charge. That means this x node is going up. So with respect to x node, you are getting the comparator output, but comparator output you are going to check only when your x is this much. This is what this question is saying. So at what time you are getting this x, that I am calling as t1. And what is your t1? t1 is your conversion time. And what is the relation we got for conversion time? The relation we got that your conversion time should be less than or equals to sampling frequency. There you go. From there we need to find the sampling frequency. That's it. This was the question. So from the first lecture onwards, when you are studying ADC, I told you one thing, that in the end I will tell you the meaning of sampling, why sampling is required and how to solve the questions based on sampling. So yeah, this is the last video of our ADC and here I am telling. In the first video only I told that there will be sample and hold circuit which will be used, and once we have the stable VA we will get the digital word output. So here also the same thing is happening. What we are taking as a stable VA, that is this value. If we are having this value, at that time we can give the comparator output, and based on the comparator output this digital logic will give us a digital output. Are you able to grasp this point? So all these things we are going to write down now. Okay. So if you are not able to understand, slowly you will understand. Okay, again we are going to write it down. So let it be here. Let this much of thing be here. Now I am going to draw it. That this is my V in. I am having a resistance of 75 ohm. This I am calling as R. Okay. And this is my node X. This node X is actually fed to all the comparators, where positive node is connected to Vref and negative node is connected to this X potential. Okay, and based on that we will receive the output, and then there is this digital circuit. There is this digital circuit which is giving us corresponding digital output. So this is our complete structure which is given. So this node X, this capacitance is 255 into 8 picofarad. This is the capacitance. So now this node X will charge. So how this node X will charge? In this manner. V full scale 1 minus e to the power minus t by RC. And at what time it will, what we need to find? Ideally it should be V full scale, but we can have the error of plus minus half LSB. And the time when we reach it, that time is T1. And here T1 is your, T1 will become your conversion time. Why T1 is becoming conversion time? If this particular block, this thermometric code binary conversion would be having some delay. Let's just say this is having some delay of 2 seconds. So what will be your conversion time? T1 plus 2 seconds, right? Here we are assuming this comparator is not having any delay, this is not having any delay, further circuit is not having any delay. This is what we are assuming. If this code converter was having some delay or this comparator was having some delay, then that delay would have been added. But here T1 will become conversion time, because delay of other components are 0. So what do you mean by half LSB? What is the LSB? LSB is resolution. I told you this thing. LSB is resolution. Now tell me one thing. Can it ever go above VFS? No, it can never go above VFS. No, it can never go above VFS. It has to go below VFS only. So positive sign is needless, right? So we will take the negative sign. And what is your LSB? V full scale divided by 2 to the power n minus 1. How many bits are there? If there are 255 comparator, then how many bits should have been there? You could have analyzed by looking at the output bit, but they are not making the output bit. They have only shown 2 bits. It is certainly not 2-bit flash type ADC. It is 8-bit flash type ADC. How you can say so? Because there are 255 comparators. So what is the number of comparators? 2 to the power 8 minus 1. The number of bits are 8. So it is a 8-bit ADC. V full scale 1 minus e to the power minus T1 by RC. So n is equals to 8 here, n is equals to 8 here. So I will put the value of n equals to 8 and we'll find the value. So shall I show you the calculation, or you can do it on your own? I think you should be able to do it on your own. VFS will get cancelled. Let's write down one more step, otherwise people will be getting confused. 1 minus 2 into 2 to the power 8, what that would be? 256 into 2, that would be 255. 255 into 2 would be what? 255 into 2 would be 510. 510. V full scale is getting cancelled. 1 minus e to the power minus T1 by RC. I hope now you can solve on your own, right? So now I will solve the value and find the value of T1. Mark that R value is 75 ohm and C value is this much. Okay, so I will solve it by pausing the video and write down the answer. So after solving it, I am getting T1 equals to 0.953 microsecond. That means your sample and hold circuit should give the window of at least 0.953 microsecond so that it becomes stable here and then give the corresponding outputs. So you need a window of at least 0.953 microseconds. Did you understand this point or not? So I need a window of 0.953 microseconds. So what is the conclusion? That my sampling time should be greater than 0.953 microseconds. This is the sampling time. This should be greater than, or in the worst case, equals to. So you can just take the reciprocal. I just need to find the sampling frequency, right? What they are asking. Sampling rate or sampling frequency? Sampling rate. So just take the reciprocal of this. So what I am getting? 1.04 megahertz, or I can say mega samples per second, right? Basically here what was my sampling time? 2 seconds. So what will be my sampling frequency? Half. That means I am taking half sample per second. Half sample per second. What do you mean by that? In 2 seconds I am taking one sample. Half sample per second. What do you mean by that? In 2 seconds I am taking one sample. So in 2 seconds I am taking one sample. So sample per second also could be unit, or you can say hertz as well. Okay, you can say hertz as well. So you can say 1.04 megahertz. So your Fs should be less than 1.04 mega samples per second. And what is the option? 1 mega per sample per second. Okay, so Fs would be 1 mega sample per second. Okay, if I had been the question paper setter, I would have put one of the option as 1.6 mega sample per second as well. Okay, then what people would think that 1.04 is near to, okay, not 1.04, 1.06 I would have put. So they would think that it is near to this, so this should be the answer. No, your Fs should be less than that, and there is only one option. There is only one option. If it was the scene that there is option available 0.5 mega sample per second, then that could be also correct. Okay, here they are asking closest, but what they would say that which all are the maximum possible sampling rate. So anything less than 1.04 will work. So 1 mega sample, 0.5 mega sample per second. So I hope you must have understood the concept here, that what is the core concept, that first there is a sample and hold circuit. So you should give at least conversion time to that, so that it can convert it, then you should apply the next sample. So basically let's just say if this was my input, if this was my input, and first sample I am collecting at T1, then at least I should give a window of 0.953 seconds microsecond to collect the next sample. Then again this window to collect the next sample. Then that sample would have come here, and it would take 0.953 second time. Basically at T equals to T1, let's just say at T equals to T1 you are having V in voltage. So that would take 0.953 second time to reach there, and you will receive a digital output. And in the meantime, V in will also receive another sample. So again 0.953 microsecond it will take and will give the final output. And in the meantime, V in will receive another voltage. So that process will go on. Sample and hold circuit will give voltage to V in, and V in will give voltage to the negative terminal of op amp, negative terminal of comparator. So that process will go on 0.953 seconds, 0.953 microsecond, and you are receiving the output. So that's the thing. So that's it about this question. But there is one more interesting thing. which is not usually taught, but we will see this block. Usually what do we use here? What do we use here? When you study the standard flash type ADC, what do you use? Priority encoder. Priority encoder. 2 to the power n, priority encoder. Now what is this thermometric code converter? Thermometer you can say, or thermometric code to binary conversion. What do you mean by this thermometric code? So once you go into the industry, once you start working in the DAC team or ADC team, there you will be using this thing. What is thermometric code? So let me explain you. It is not relevant to your gate examination, but yeah, if they have given this particular block, then who knows, they can ask this question as well. Okay, they can ask this kind of question as well if they have given the block. So what is the meaning of thermometric code? So that we will understand by an example. Okay, so you know what is a binary code? You know what is a binary code? You need to find me the equivalent resistance R equivalent with respect to these binary codes. That means if B0, B1 and B2 all are 0, 0, that means all are open circuited. So what will be the equivalent resistance? Infinity. All are open resistance. All are open circuited. So equivalent resistance is infinity. And this is your this is your conductance. This is your resistance. Okay, resistance, conductance. So that is 0. 0, 0, 1. That means this is on. Sorry, equivalent resistance will be R. Okay, this G we will write. No need to worry. Now only B1 is on. This is decimal equivalent 1. This is decimal equivalent 2. So only B1 is on. We are going line by line. Now decimal equivalent 3. So if both are on, what you will get? R parallel with R by 2. R parallel with R by 2 is equivalent to R by 3. So R by 3. 1, 0, 0. Next you will get R by 4. 1, 0, 1. Next you are going to get R by 5. Basically R by 4 will come in parallel to R. R by 4 come in parallel to R. What you are going to get? R by 5. Here you are going to get R by 6. And if all come in parallel, you are going to get R by 7. So here your resistance is not linearly increasing, but you can see your conductance is linearly increasing. If conductance here is G, then what it would be? 2G. Here it would be 3G. R by 2 is the resistance, then what will be the conductance? 3G, 4G, 5G, 6G and 7G. So what do you see? It is linear. Linearly it is increasing, no? With respect to bit, it is linearly increasing with step size of G. Right? It is linearly increasing 0 to G, G to G, but it is not linearly increasing. R by 2, R by 3. This is not linear relation. This is the linear relation. Now, if I need to implement the same circuit using thermometric code, what I will do? I will connect same kind of resistance in parallel. Okay, 7 same kind of resistance in parallel. And how I will start? Once I will not connect any of the switches. I am just telling you the meaning of thermometric code. That is important because the question has come. So R equivalent will be infinity and this will be 0. If T1 only is on, so what will be the R equivalent? R, and G will be, I am calling as G. Now the next what we are going to do, if this is on, we will keep this as on only. If one has become on, we will keep this as on only. So what we are going to do now? Next I will turn this one on. So R by 2, 2G. Now if these two are on, we will keep these two as on only. Next I will turn this on. So R parallel with R parallel with R, 3G. So if your design does not allow you to make R by 2 and R by 4, if you are not able to make R by 2 and R by 4, you are only having the resistance R, then you are going to use thermometric code, not binary code. Let's just say in my design I need linear resistance. I need not linear resistance, sorry, I need linear transconductance. I need 0, G, 2G, 3G, 4G, 5G, 6G, 7G. This is what I need in my design. Somewhere I need this. And I only have the resistance R. If I only connect resistance R here and go with the binary code, what will happen? First only this R will turn on, so R you will get. Then next this R will turn on, again R you are getting. Then both will turn on, then R by 2 you will get. Very random it will be. Very random. So in that case what you need to do? You need to use thermometric code. Okay, this is just a depth I am telling, which is not required as per the question, but this block was given. So people will have the doubt of what is the meaning of that block, so that I am telling. So yeah, what we were doing. So here 4 will turn on, so R by 4, then all 5 will turn on, R by 5, 6 will turn on, R by 6, and then R by 7. So 4G, 5G, 6G and 7G. So both are serving the same purpose, you know. So what I can do, I can relate this thermometric code to binary code. This is how I am gonna relate. So 000 was equivalent to 000 only, because you are getting both same. G equivalent was 0 only, and 0001 is equivalent to 0001. This was equivalent to 010. This was equivalent to 011. This was equivalent to 100. This was equivalent to 101. This was equivalent to 110. This was equivalent to 111. This truth table doesn't look like priority encoder or not. Yes, it is like priority encoder only. If you are clicking on T1 button, do not think about if I have clicked on T1 and do not click on these buttons, then output will be given with respect to this decimal equivalent, which is 001. If I am clicking on T3 button, do not think about these two. Output will be given with respect to T3 only. So 100. And what is the good advantage here? In case of priority encoder, this 000 will give you don't care here. Say yes or no. Do you remember it? In case of priority encoder, if you are not clicking on any of the button, then at the output you will get don't care, not 000. And don't care can take value 1 as well. And if they take value 1, then that would be our issue. Basically, this is my final output of the ADC. So let's just say at the all the comparators is giving me 000, all the comparators which are connected. I am not taking the example of 255 here. There are 255 connected. So if all the comparators are giving me 000, and if I use priority encoder, then 000 will give me output as don't care. And what if my don't care take 110 value? So what user will think? That here 110 you are getting, that means 6 must have been applied. So that would give you wrong output. But if you use thermometric to binary conversion, there you see that you are getting correct output. That for 000 you are getting 000 only. So you can use this block as well, thermometric to binary. Are you getting this point? So that's why they use this block, and this is the meaning of thermometric code. With an example we understood where we are going to use thermometric code and how they are equivalent. Okay, if you need to study deep about this ADC, this kind of ADC, there is thermometric ADC as well, there is binary ADC as well. So if you need to study deeply about that, you can go to the lectures of Shanti Pawan sir. Okay, Shanti Pawan sir has a course on data converters that you can watch. But as a GATE aspirant, even for UG guys and even for PG guys, I do not recommend that. That course is very tough. Okay, I have tried studying that course. I haven't completed that, but somewhat I have studied that. Okay, that data converters course that is related to analog VLSI. Once you go into the industry, there will be, if you be analog engineer, there will be a team of DAC and there will be a team of ADC as well. Certainly there will be these two teams, and for these two teams that course is like a must. Everyone should study that course, but that is the thing of later on. Just now I am telling it just for your information. So if you want to study, you can go there. It would be in the last, okay, in the last lectures you will see this thermometric DAC and binary DAC that you can see. I am talking about DAC, not ADC. Thermometric DAC and binary DAC. There you will be using this configuration. So from using his reference only, I am telling you the expression. What do you mean by thermometric code and what do you mean by binary code? Okay. So I hope you must have understood each block of this question. What is the meaning of accuracy of half LSB? What is the first block? Why they are asking the sampling frequency? What is the meaning of sampling frequency? Why this block is used? How it is giving us digital output? And what is the use of these capacitance? How they are coming in parallel? All kind of things. Every single thing related to this question has been clear to you, right? So with this we end our A to D converters. Now to my YouTube subscribers, if they want me to bring whole data converters on YouTube, I have taught it for 7 to 8 hours and I can guarantee you this would be the best ever D2A converter you would ever study, at least till UG level or at least till GATE level. So if you want me to bring, I am asking you to share this video. If this get good response, then I would be happy and we will be bringing the next marathon on A to D converters or D2A converters, basically the complete data converters I can bring. So the demand is you need to share. Okay, if we get good subscriber, if I get good motivation, if I get the good response, then I can think of bringing the complete marathon. Okay, thank you very much. Now we are going to start CMOS VLSI. We can start, or logic family we will start. or we can start PLDs. So that I will see what I need to start, and we will cover it very quickly. Now 2 to 3 lectures are remaining. That's it.